In this video, I'm going to show you how to connect other sources of power, such as batteries, wall adapters, and I'll discuss a little bit about connecting the power from the computer. I will also talk a little bit about how to regulate the power and how to smooth the DC voltage. But before we can do anything, we need to look at the datasheet for the components that we'll be using. Up to now, we've only been really using the AVR microcontroller. We've also been using LEDs, but we've been adding a resistor to resist the current going to the LED, so the LED would be within its working bounds. From this point forward, however, we'll be adding other peripherals to the AVR, such as accelerometers, servos, other motors, MOSFETs, which we'll talk about later, other integrated circuits, rangefinders, and possibly a GPS. We may get into many other peripherals, and each of these may have different power requirements. Right now we're just going to focus on the AVR microcontroller and see what the power requirements are. At this point, we're only going to be concerning ourselves with voltage and less on current. Generally, these devices will have a limitation on the current, but what you connect with the devices, they will have a variety of different current draws, or how much load or current it will require on its own. We'll be looking up the data sheet for the Atmega32 and the 324. The 324 is the newer version of the 32, and it actually has different power requirements. Regarding power, the difference between these two microcontrollers is that the standard 32 can receive power between 4.5 and 5.5 volts. The 324 can actually receive a much greater range of voltage, from 1.8 volts to 5.5 volts. That's actually the 324A. The 324P actually receives a lower range, actually from 2.7 to 5.5. But since most peripherals range between 3 and 5 anyway, this is a perfectly appropriate microcontroller to use with these tutorials. You'll want to adhere closely to these ranges as much as possible. You don't want to go below the minimum voltage, because obviously you won't be powering your device. And you don't want to go over the 5.5 because you might cause the chip to be damaged. On pins 10 and 11 are the power pins, the two power pins for general operation. There are other power pins, but that applies to the use of the analog to digital converter. Pin number 10 is the VCC pin, and pin number 11 is the ground pin. According to the datasheet and the Atmel's application notes for power, it is really important to put a capacitor as close to these two pins as possible, because there's a high current loop. If you put the capacitor far away, then the high current loop becomes larger, and high current spikes can form in that loop. Make sure to put the decoupling capacitor, which is the capacitor we used in previous tutorials. And the value of this capacitor is recommended at 100 nanofarads or 0.1 microfarads. So let's talk about batteries for a moment. The things to consider about batteries is that there are different types of batteries even in the same container. This particular battery is a rechargeable battery, but it has a different voltage than a standard AA battery. For this battery, which is nickel metal hydride, it has a voltage of 1.2 volts. This battery, which is a standard battery of AA alkaline, is 1.5 volts. And also, through time, batteries change in voltage. This is time, and this is voltage. And let's say this is the 1.5 volts. Through time, and when the battery starts to run down, it will begin to have a slope downwards, where when the battery runs out of charge, the voltage actually goes down. And also, depending on how the circuit was put together, the DC voltage may actually fluctuate a little bit due to interference. On a battery, you'll have a plus side and you'll have a minus side. And these batteries can be connected in a serial fashion, which means they would be connected in a line like this. The positive would be connected to the negative side, and you can keep going with that. And the voltage will just increase as you go. So this would be, if you had three batteries in a line and you connected terminals to check the voltage on each side, you'd have 1.5 volts times 3. So 3 times 1.5 equals 4.5 volts. Let's check to see if this is actually what we're getting. I have the 3 batteries in line. I'm setting the meter to voltage. And I'm just going to check, make sure that you have your red on your plus and your black on your minus. Otherwise you'll just get a negative number here. So we should be getting 4.5 volts. Let's check. It looks like we're getting 4.8 volts. Or 4.7, around 4.8 volts. And this is a good reason why we would want to have circuitry to regulate the voltage coming into our circuit for the microcontroller, because we want to have a constant voltage. And you also have batteries of different form factors. You have the AA, you have the AAA, you have like a watch battery, and you have a 9 volt, and you even have the size C and size D. And generally, but not always, size of the battery will determine the length of time that it will last under a constant load. And size generally doesn't determine voltage, because this little tiny one right here is 12 volts and this one is 9 volts. And you'll also find these batteries inside of other batteries just stacked up. Wall adapters are plugged directly into the wall using a standard plug like this for, I guess this would be US, and generally 110 volts, 110 through 120 volts. And, or you can, I guess for other countries would be 240 volts. And they have an input voltage of around 120 volts. You can see the input voltage 120 volts. And then you have an output voltage of a DC voltage. This is 9 volts. This one would be actually fine to use because I'm going to discuss how to regulate this voltage. And 9 volts is actually not that bad. We can actually use this, even though it's higher than the voltage of our device. And the other end of the AC wall adapter will have a plug like this. I generally just cut this off and use the 2 wires. And DC output, you'll have a plus, which is the rated or the stated voltage, and you'll have a 0 volts, which is ground on the other one. The AC adapters may already have its own form of regulation, but you don't know what the circuitry is, so it's always a good idea to create a circuit of your own for regulating the DC currents. Some of the major considerations that I have come across in my experience determining whether to use the wall adapter and batteries is you only want to use batteries if it's going to be a device that cannot be plugged into the wall, because the batteries are very expensive and wall adapters are really cheap to use. Just to give you an example, I am paying for my house about 13 cents per kilowatt hour, and you're actually getting about 1500 milliamp per hour for a particular battery. You might be getting a little bit better with rechargeable batteries, so I would actually consider using rechargeable batteries, but you're gonna have to use more because these are 1.2 volts as opposed to something of the same size, 1.5 volts. And if you're using batteries, you'll need a way to hold the batteries. And in these types of battery holders, you have the batteries configured from negative to positive, then negative to positive. You'll see that there's a way to connect the negative pole to the positive pole to the next battery, and so on. And these come in different configurations. You have this one that holds 2, 4, 6, 8 batteries. This one holds 8 batteries as well, but has a different form factor. You have ones for little watch batteries. You can just put them in here. And you have ones that are enclosed and even contain an on and off switch. They will all have a positive and negative lead to be plugged into your project, your circuit. These have a very familiar type, like the 9 volt connector, and these would connect to something like this that has 2 leads. And they would just be connected like this, and you have the 2 leads. And the red one would be positive, and the black one would be ground. For lower voltage needs, you'd have a holder that would only have 4, and this one also probably has 4. And what I like to do, just for prototyping, I like to solder a header to the 2 lines. You might want to use heat shrink or something or silicone or whatever to make sure that these 2 lines do not connect, because that would be not a good thing. And this header would be able to be plugged right into the breadboard. Because of the various voltages that we can get from batteries, and that the batteries are 1.2 or 1.5 volts each, you're not going to get the exact voltages that you want. So it's best to use a voltage regulator that allows you to output your desired voltage. A regulator cannot take a voltage that is lower than what it will be outputting. It must be a much higher voltage than it's going to output. And there are different types of regulators. One that has a low dropout, which are these 2, and one that has a high dropout. And dropout really just means that you must give it a much higher voltage than what it will output. With a low dropout, you can give it a voltage that's much closer to the output voltage. The three that I like to use is for the voltage regulator, and this is a high dropout, is the 7805, and that will provide 5 volts of output voltage. I also like to use the Max 603 and 604 voltage regulators, and these are low dropout, which you can provide a voltage much closer to the voltage of its output. And the 603 will output 5 volts, and the 604 will output a 3.3 volts. And the 3.3 volts, it's different from the 3.0 volts. This is actually a standard voltage range for a lot of components out there. Even though these are considered regulators and they create a particular voltage, you still need to filter some of the spikes that will happen, or some of the interference that could happen in the circuit. So we're going to be using capacitors for that. We'll use a combination of electrolytic capacitors and ceramic capacitors. Generally, the pin configuration is like this. This is the input pin, this is a common or ground pin, and this is an output pin. So the input pin would be the voltage would be going in, and this would be, let's say, somewhere around like 8 volts or something like that, 9 volts. Let's just say it's 9 volts. And the output would be 5 volts. But we have to add the capacitors that would filter the actual voltage and get any spikes out of it. On the input side, you'll want to use a 10 UF capacitor, and it'll be a polarized one, so you'll want the negative side on this side and you want the positive side on this side. And on the output side, you'll want a 0.1 UF, similar to the one we're going to be using on the actual microcontroller. And this is generally non-polarized, it's a ceramic capacitor. For the 7805, you can put in generally as low as 8 volts to get 5 volts out, and as much as 30 volts. But the higher the voltage, the more heat is going to be built up on this device. So if you're going to be using higher voltages, you'll want to use a heat sink on the back of this, where the metal is located on the back. And heat sinks are generally just a piece of aluminum that has a profile that looks like this. And you've probably seen them on computer chips or devices like that, and it draws the heat away from the actual device. So let's connect this one up to a breadboard and check the voltages that we get. Select a good location on the breadboard, and we'll take our 7805 and just plug it into a free section of the breadboard. And because we know that the middle is ground, we will take our 10 UF capacitor, and you'll see the negative side. It has a black stripe on it with some negative symbols on it. We know that that side is going to go to the middle, and we're going to connect the other lead, the positive lead, to the input. Then we'll take a tiny 0.1 UF capacitor, just this little device here. And I'm just going to bend this back a little bit so we can see everything. And this is non-polarized, so you can put it any which way around. And we're going to be putting it to the negative side, which is we're going to be putting it to the ground and to the output pin. And next we'll need to connect the ground to the ground, the output to the positive side, and then we'll connect the battery to the ground as well, and a lead to the input side. I'm going to connect this already made battery connector with the header already soldered on. I'm going to connect that to this point, and I'll connect the battery afterwards. So we want to make sure that the black wire goes to the ground and the red goes to the input. I'll now put a wire from the ground pin to the ground, or to the negative rail. So I have from the middle pin, I have that going to the negative rail. And now I'll take a wire that goes from the output pin, which is the 5 volts that we want, and we'll connect it to the plus side. So now you can see that there is a regulator, 7805. We have a 10 UF capacitor that is put in the correct way, the correct orientation, between the input and the ground pins. And we have a 0.1 UF capacitor that is placed between the output and the ground pins. We have our connector for the battery, on the input and ground, and we have the ground connecting to our negative rail, and we have our output, which is the 5 volts that we want, to our positive. From the previous circuits, we know that we already have these connected to the plus and minus already, and at the VCC and ground we already have a 0.1 UF capacitor really close to the pins, as close to the pins as we can get them on this particular breadboard. Now if this is a good device, a 7805 is working properly, we should be able to power up our entire circuit, and we'll get the output that we did in our last tutorial on the LCD. I'm going to turn this around so we can see the LCD in its proper orientation. I'm going to plug in the battery, making sure it's on the right side, because if I plug this battery in backwards, just touching it, I could potentially take the electrolytic capacitor and I could destroy this capacitor. In some cases, if it's done long enough, this capacitor will actually explode. So you want to be careful with that. So let's go ahead and plug the battery in. And you can see that the circuit is working fine. Let's go ahead and test the voltage we have on those 2 rails and see if it is actually 5 volts. Because my leads won't be able to go into the breadboard, I'm going to have to just touch the red on the output. I'll just do it on the output capacitor. And I'm going to see if I can get the ground. I'll just use the ground here. And I'm getting 5.02 volts, which is lower than 5.5 volts, and you can see it's constant. It doesn't fluctuate at all. Now let's use a lowered voltage source to see what happens with the regulator, see what voltage output we get. And we have 6.26 volts, and it's steady. I've been using these. Now let's connect it, and we'll see what voltage we get out. I can see that the LCD is still working, but it's faint, so I'm getting a 4.74 steady voltage. I'm going to write that down, 4.74, and we started with 6.24 while it's connected, and this determines our dropout voltage. This is our voltage going in, and this is our voltage out. So this is 0, 5. So our dropout voltage is 1.5 volts. This still may be enough to run the circuit, depending on the circuit. You can see that the circuit is actually still running, but you can see that it's quite faint. You can barely see the X running across, and you can see that the X and Y numbers here are faint. And if we adjust the contrast, we might be able to see it there. So even though we have a lower voltage, we can still make it work, but we have to adjust the contrast on the LCD and maybe do a few other things. But it's better to get a much higher voltage and have a constant 5 volts coming into the circuit. My preferred regulator is actually the Max 603. With the Max 603, the dropout is a lot lower, so you can actually use a voltage source that is closer to the actual voltage that you desire in your circuit. The input pin is located at pin number 1 at this location, and you have an output pin which is located here. You also have many options for ground. So you have both of the middle on each side ground, and these 2 are ground. The 4th pin on this side is called the off pin, and if this is connected to ground, then the chip is deactivated. The off should be connected to the input voltage to activate the chip. So this is just going to be connected to the input voltage. And on the other side we have a pin called set. And if this pin is connected to ground, then we are establishing the output voltage set by the chip. Otherwise, we can actually modify the output voltage by connecting resistors on this pin. But we're going to stay with the voltage that the chip was set. In the application notes, it recommends putting a capacitor between the output and ground, and a capacitor between input and ground. And the capacitor values are 10 microfarads. Let's connect this to the breadboard and test the voltages. We'll start by putting the regulator in the breadboard. It doesn't really matter which way you put it in because we're going to be wiring it. Since this is the in and the ground, the first 2, the number 1 and number 2 pin, I have the number 1 pin over here. This is the way I oriented it. You can also tell by a little notch that's on one end, and sometimes it'll have a line along the IC, and sometimes also it'll have a little dot in that number 1 pin place. Red in my power means the plus side and the black means ground. So I'll just put this in. According to the data sheet and the application notes, we have to put a 10 UF capacitor between the power and the ground. That's the power coming in. And we need it on the other side. We'll put the other capacitor output. This is the output, VCC, and this is the ground. And we need to also put connect set to ground. We need to connect off to the plus side. So we're essentially turning on this regulator, and by putting set to ground, we're using the 5 volts that this is essentially designed for. Okay, now we're going to be connecting the set pin to ground. So we're using the default voltage output of 5 volts. Now we're going to connect the off to the plus side, so we're enabling this little IC. So we're enabling the regulator. Okay, so now we have the off connected to the input voltage. Now we can wire the ground and the output to our negative and positive rails. We'll start with our negative. Let's go positive first. So we have our positive output pin to our plus rail here. So now we'll put the wire from the ground pin. I can do it from either one of these ground pins here. Since both of these are ground, I can go from here to the negative rail or from here to the negative rail. I'm going to put it to this one here. Looks like I hit that lead. Okay, so I have the ground from the ground pin going to the negative rail here. So now I should be powering my breadboard with the correct output power. Now all I have to do is connect the external power, my batteries, to the circuit. I'm going to start with a 9 volt and see what voltage I'm getting. If you want to test the voltage before you put the battery on, you probably don't want to connect these 2 lines yet. I'm going to connect them because I already know they work, but if you're putting this together the first time and you don't know whether this IC is good or not, it's best not to plug it into these rails yet. You can test the voltage coming out first before you do that. And then once you know that you're getting a good 5 volts or within a pretty good range of 5 volts, you can go ahead and plug it in. So I'm going to go ahead and plug it in. And I am getting something on the LCD, which is good. I'm going to go ahead and test the output and see what voltage I'm getting. Okay, I'm going to touch the ground and with the black lead, and I'm going to go to the lead of the capacitor, and I'm getting a 4.96 volts, which is well in the range of operating. So that worked. I'm going to plug in my lower voltage batteries and see if that still works. The LCD is working at the same contrast level, which is what we didn't have on the other regulator. And let's see what voltage we get on this. 4.96. So we get exactly the same output voltage with the lower voltage batteries. With wall adapters, you would use the same circuit here, which is the voltage regulator, either one, the 7805 or this one. This one was actually made specifically for batteries. Maxim created this integrated circuit, so it would take advantage of the using lower voltage batteries. And with a low dropout, so you maintain as much battery voltage as possible. But you would take this essentially, if you wanted to just prototype, I would just get a wall adapter, and you could essentially either get one of these connectors and then put it into your board, or you can just snip this off, separate the 2 wires, strip them, so you would expose the wires underneath. Test the wires, make sure that you know which one is the positive side and which one is the ground, and put them in the appropriate locations in the circuit so you don't cause any problems with your microcontroller or this IC or your electrolytic capacitors. You could also do the same thing even with the computer power. With the computer power, you would essentially plug it in like you would be plugging in our interface to the programmer, but you could also take a USB connector. With the USB cable, you would expose the the wires, you'd have blue, white, red, and black. And the red and black are the power wires. These two, white and blue, are data lines, or D plus and D minus. You can expose these red and black wires. The red would be the plus side, and the black would be ground. And you can actually plug this straight into your circuit. This is the other side of the plug where you plug this into the computer. And then you have a good 5 volts coming out of this. And you would essentially need to plug this straight into your circuit without using a regulator, because the computer essentially has a pretty good regulation of voltage coming out of it. But putting 5 volts into a circuit like this, you wouldn't be able to get 5 volts out, because you'd have to have something higher than 5 volts. So you'd essentially have to plug this right in. But you could plug this into a 3.3 volt regulator and have that 3.3 volts come out from the output of this regulator. So those are the options of using different power sources for your circuits in microcontroller circuits and design. And I've given you options for using battery, wall adapter, and computer, and shown you different ways you can put batteries to the circuit, powering the microcontroller using 2 different types of voltage regulation, one for low dropout and one for high dropout voltages, and the proper ways to connect these voltage regulators to the circuit. Thank you for watching.